All right, so this will be walkthrough for exam 2, version A. Um, Jump into it here. Actually, first question I'll write out. There we go. So the first question, it wants to find the osmotic pressure for a 0.460 molar sodium chloride solution. It's at 55 degrees C, and our Van Hoff factor is 1.9. So our osmotic pressure is going to be equal to the molarity times the gas constant times the temperature. And in this case, since it's the molarity of the solution, it's how many moles of solute particles do we have. So we would need I to factor into that molarity. So I'm going to take my Van Hoff factor times my molarity. Times the ideal gas constant. We're dealing with pressure. So we're going to use the 0.08206, which is liter atmospheres over mole Kelvin. And we're going to multiply that by the temperature. Units in the ideal gas constants are Kelvin. So I need to use the temperature in Kelvin. So 55 plus 273 is 328. So that should give me 23.52 atmospheres. All right. Next question. There we go. Determine or give the characteristic of a first order reaction having only one reactant. So I'll go back into the whiteboard here. If we have a first order reaction, all of these are talking about the rate of the reaction. So that's going to be our rate expression. So rate equals K times whatever the reactant is in its first order with respect to that reactant. So the rate of the reaction is not proportional to the concentration of the reactant. Well, that isn't true. If I double the concentration of A, I should see the concentration doubling. If I triple the concentration of A, I should see the concentration triple. So it is somehow related to the concentration. It's proportional to the square of the concentration of the reactant. Well, no, because if it was proportional to the square, then if I double the concentration, I wouldn't see it double, I'd see it quadruple. It's proportional to the square root of the concentration. No, because, whatever, if we quadrupled it and it was proportional to the square root, that'd be 2. That's not what it actually does right here. Oops. Yeah, it's highlighted. I don't like that color. Some pretty colors. Nobody knows. Oh, well. Yeah. Well, we'll just do that. Yeah. This is what we should see. Rate of reaction is proportional to the natural log of the concentration. No, the rate isn't. Plotting the natural log of the concentration, if it yields a straight line, will tell us that it's first order, but that is actually not involved in the rate expression itself. And lastly, the rate of the reaction is directly proportional to the concentration of the reaction. Yes, double the concentration, double the rate, triple the concentration, triple the rate, quadruple the concentration, quadruple the rate. So it is directly proportional. So that's the one we have there. For the next one, we have for the reaction A to B, we record the change in reactant A versus time. Then we plot 1 over that concentration versus time, and this plot gives us a straight line. What can we determine if we do get a straight line plot? When we plot those specific parameters, then we know the reaction is second order with respect to that reactant. Don't necessarily know if there's other reactants, don't know what order it is with regards to those, but we do know with respect to A that it's second order. This is similar to the question from your practice exam, but there we were told it doesn't give a straight line, so it wouldn't be second order, but in this case it does. Changed one little part of that there, so now it is second order. Calculate Kp with respect to, there we go, that reaction. So I've got N2 gas plus 3H2 gas, and that goes to form 2NH3, and we're told Kc in this case, and that is 3.7, excuse me, times 10 to the 8th. So our equation here is Kp equals Kc times RT raised to the delta N. Delta N is the number of gas molecules on the products minus reactants. So delta N equals our 2 NH3s minus our 3 H2s and our 1 N2. So delta N should be minus 2. So this should look like 3.7 times 10 to the 8th times 0.08206. We were told this was at 298 Kelvin raised to the negative 2. 0.08206 times 298 is 24.45. This is essentially the same thing as when we take that times 10 to the negative 2, we could rewrite that as 1 over 24.45 squared. And that would give us 3.7 times 10 to the 8, and that should be about 597.8. And we get 6.19 times 10 to the 5th in that case. Yep. So answer A for that one. Uh, of course, they updated Zoom, and now it seems crappier. All right. Next question. They want to know what are the units for our rate constant for the following rate expression. In this case, our rate expression is rate constant times concentration of X raised to the first order. So it's first, or raised to the first power. So it's first order overall, first order with respect to X. That's the only component here. So if it's first order, those brackets mean molarity. So we're going to have molarity raised to the first power. That's going to be units of molarity. And then whatever the units are for K, we're always going to try to express that rate as molarities per second. So what do I multiply molarity by to get molarities per second? 1 over seconds times M gives me M over seconds. So 1 over seconds, or seconds to the negative 1, that is my units for my rate constant in this example. Back to this. Calculate the value. Okay, here we go. So we're given the overall reaction equation. It's balanced. we're told that K is equal to 2. And in this case, we're given equilibrium concentrations for 3 of these things. Remember, the equilibrium expression is products over reactants, not the other way around. So it's going to look like this. And we have, in this case, so our actual value for that, that's 2. We know our actual value for the NH3, 0.5. That's going to be squared. We don't know the concentration for the N2. That's what we're trying to find. We can make that X. And we do know the concentration for the H2. That's 1.5. And we know that's going to be cubed. So we're going to get 0.25 over X times 3.375. So what I can do is multiply, actually easier way. Oh, God damn it. Oh, selected eraser. There. We'll multiply this by X. So that'll cancel that. And we'll multiply our 2 by X. So I have 2X equals 0.25 over 3.375. I could take 0.25 divided by 3.375 and get 0.074. Divide both sides by 2, and X equals 0.037. All right. Next question, calculate the freezing point of a solution that is 300 grams of ethylene glycol, that's C2H6O2, in 600 grams of water. And we're given our KF and our KB, but we want the freezing point, so we're only going to use the KF. We need to find the molality, so that's going to be moles of C2H6O2. So I'm going to take 300 grams divided by 62 grams per mole. That's going to equal, there we go, 4.8387 moles. Yep. And molality is moles over kilograms of solvent. So my 600 grams becomes 0.6 kilograms. And that is 8.0645. We do not have a ionic solution, so our Van Hoff factor is 1. So I've got 8. I can just leave the 1 out. 8.0645 times my freezing point depression constant, 1.86. That should be 15. And I want to subtract that from my normal freezing point. My normal freezing point is 0 degrees Celsius. Subtract our freezing point depression, and our new freezing point should be lower, should be negative 15 degrees C. Which of the following statements is true? If Q is less than K, it means the reverse reaction will proceed to form product or to form reactants. No, if Q is less than K, then we haven't reached equilibrium yet, so the reaction should still be proceeding in the forward direction greater than the reverse. If Q is greater than K, it means the forward reaction will proceed. Nope, if Q is greater than K, it means we've gone beyond equilibrium and the reverse reaction will actually happen at a greater rate. If Q is equal to K, it means we're at equilibrium. Yes, that is correct. And of course, since only one of these is correct, then neither D or E is possible. For question 9, The dashed lines represent our solvent and solute, red for the solvent, blue for the solute, and then the topmost dashed line below the purple one here is going to be your solution. In an ideal solution, we are looking at the straight lines, the dashed lines. Our actual has a larger vapor pressure than predicted, so that would mean the solution would have weaker solute-solvent interactions to give us that greater vapor pressure. The equilibrium constant for a specific reaction is 1.4 times 10 to the negative 5. This is similar to one of your practice exam questions, but there it was 10 to the 5, so it was a very large number. And in this one, it is the negative 5, so it is a very small number. If K is very small, that means the number on the top, our product concentrations are noticeably smaller than the number on the bottom, our reaction concentrations. Therefore, we have C at equilibrium. The reactant concentrations are greater than the products. Equilibrium only tells us the concentration of the products and the reactants at equilibrium. It has nothing to do with the rate. That's the rate constant, the rate expression, completely different, completely separate. We will know what our concentrations are at equilibrium. We don't necessarily know if it is a fast rate or a slow rate, though. So we'd have no way of knowing A or B. All right. Here, activation energy. So we're going to use the Arrhenius equation for this one. Arrhenius equation is rate constant equals our frequency factor, and then E raised to negative activation energy over the ideal gas constant times temperature. So in this case, our activation energy is 103 kilojoules. We want to use the R relative to energy. So we're going to go from kilojoules, or I'm going to anyway. You could do this later or differently, but I'm going to convert from kilojoules to joules. So I'm going to rewrite our 103 kilojoules as 103,000 joules per mole. That's going to be over R. I want to use, again, the R that relates to energy. So that is 8.314. And that's joules per mole Kelvin. And then we're going to multiply that by the temperature. And our temperature now was 398 K. So actually, we should cancel all the units within here. That should give us E raised to the negative 31.12. If I plug that into the calculator, I get 3.03 times 10 to the negative 14, and I'm going to multiply my frequency factor A by that. That was 4 times 10 to the 13 reciprocal seconds. When I do this, I should get 1.21, or answer A. Question 12, biological catalysts that increase the rate of biochemical reactions. That's really the second part, just the definition of a catalyst. So what's a biological catalyst? An enzyme, C. 13. Equilibrium constants given for the reaction below. Okay, so we have, again, our D is deuterium. That's water with a neutron. Doesn't really matter for our purposes here. Goes to form H2 gas and D2 gas. And our K for that is 0.28. We are trying to get to this reaction. Wait, why did I flipped it? I don't know why I flipped it. Sorry, come on. There we go. So yeah, we're going from 6H2 plus 6D2 goes to form 12HD. And we want to find What is that, Kc? Okay, so I'm looking at this. For the desired one, I've got the HD, the hydrogen, the deuterium on the right, whereas in my exact actual equation, the one we know, the top one, it is on the left. So I think right off the bat, I probably want to flip my top reaction. If I do that, if I flip the reaction, I take 1 over K, because now the products have become the reactants and vice versa. And that gives me 3.57. Now I'm looking at these and I'm saying, hey, they still don't match, although everything's on the right side. I notice that there's 6 times as much hydrogen and 6 times as much D2 and actually 6 times as much HD. So I'm thinking, you know what? I bet I want to multiply this whole thing through by 6. And if I do that, do I get matching this reaction right here? Yes, I do. So that's what I want to do. Now, whatever factor I multiplied this through by, I raise it to that power. So I need to take 3.57 raised to the 6th power. If you think about this before, concentration of HD in the original reaction would have been HD squared. Now, there's a 12 in front of that, so I'd have to take that 2, multiply it by 6, for the reaction that we want to match, that would be raised now to the 12th power. So that's why I take that raised to that power, not multiply, but raised to that power. With your calculator, you could do a squared, and then you could do a cubed if you want to take you to that value right there. All right, next one, we've got 3-step mechanism. Our first step is fast. Our second step is slow, and our third step is fast. So give me 1 second here to write these out. Okay, so for this one, we've got Br2 goes to 2Br. That's our fast step. Second slow step, Br plus CHBr3 goes to give me HBr and CBr3. We can call that K1. I think this does K2. And that rate constant's K3. This is slow. So the second step is our slow rate determining step. However, you'll notice that, oh, here we go. That's what I wanted. These both have, come on. There we go. That Br in common. So there's 2 things competing for that bromine or bromine there. The slow reaction in the forward direction is competing for that, but the reverse of the fast reaction is competing for that as well. So I need to find the concentration of the Br from the fast step, and then I need to substitute that value in to the slow step. So the K for the slow step should simply be K3, concentration of Br, concentration of CHBr3. But when I write the fast step, I have in the forward direction, K1 times the concentration of Br2, and that's going to be equal to the reaction in the reverse direction. Oh, sorry, not K minus 1, but K2 times the concentration of Br squared. So there's my Br. I want to isolate that. First thing I'm going to do is divide it by K2. That's going to get rid of that. And then I'm left with Br but still not completely isolated because it's squared. So I have to take the square root of both sides to undo that. So then the concentration of Br by itself is equal to K1 technically to the 1/2, K2 raised to the 1/2, and then the square root of the concentration of Br2, which we will just rewrite as being raised to the 1/2. So I'm going to take this entire part right here, because that is equal to Br, and we are going to go and substitute that in for that right there. If I do that, what I have now is K1, K3 over K2, Br2 raised to the 1/2 times CHBr3. And right here I have a constant times a constant divided by a constant. I'm just going to rewrite all my little sub-constants as the actual rate constant for this reaction. So that should have been answer D there. All right. Question 15. We have this reaction here. 2 carbons in a solid phase plus my O2 gas is, should have been a double arrow, but okay, is 2CO gas, and we want to know what's the equilibrium expression. So I'm going to do products over reactants, but I'm only going to do things in the gas phase or that are aqueous. So these carbons over here that are solid are going to get left out. So I have products, carbon monoxide raised to its coefficient over reactants, but only the gaseous or aqueous reactants, which is the O2. So that should have been answer C. All right. Question 16, we have 3 steps. We're looking for the catalyst. If you go through these, you're looking at first step, CH3, CH2Br, AlBr3. Oh, this thing cut it off, didn't it? There. Second step, so you can see these are in common between these 2 steps, so that's going to get canceled. AlBr is going to get canceled here. It's produced in one step and used up in another, so that's an intermediate. The only thing that we notice that won't necessarily contribute to the products, but it isn't made in an earlier step and then used up. It's in that initial step, and it's actually regenerated in the last step, and that's that AlBr3. That's our catalyst. AlBr4 to the negative, that would be an intermediate. C6, or no, actually the C6 we would keep. And then, oh, but the CH3, CH2, that would be another intermediate. So B and D are intermediates. C and E are actually reactants and products, but A is our catalyst. 17. We've got our table here. I need to find the overall rate law for the reaction. So I want to use experiment 1 and 2 for the O3 because there I have the concentration of O3 changing. I'm going to put the higher concentration over the lower to see by what quantity did it change. That's going to be raised, we'll raise that to the n power, and that's equal to, we're going to look at those rates. So the rate for the first step related to the 0.0086 concentration is 0.0877, and for the second one is 0.439. So this should be 2 raised to the n. Oh, well, that's going to be n. And for the other one, yeah, 1.997, so really 2. So n in this case is going to be equal to 1 for our O3. And then we're going to go back. We have one other reactant still, so we need to go to there and say, hey, what trials do we want to look at? What or where is the concentration of the C2H4 changing? So that's trials 2 and 3. It's going from 0.04, or actually, sorry, it's going from 0.01 to 0.04. May notice already that's quadrupling, and that'll be raised to its reaction order M. And then our rates here are 0.1755 and 0.0439. So we have 4M equals 4. M should also be equal to 1. So to write our rate law, we're going to have our rate constant, concentration of O3, raised to the first power of first order with respect to the O3, and first order with respect to the C2H4. Next question had to do with half-lives, but they just wanted to know. They gave us the half-life and wanted to know if a certain amount of time passed, and they told us how much material we started with, could we determine how much was left over? So they didn't even tell us if it was first order, second order, zeroth order, whatever. That's okay. We won't need that. So we know we have a half-life of 33 minutes. We have 10 grams of substance and 99 minutes go by. So that means at 33 minutes, we've done one half-life. At 66, we've done 2. And at 99 minutes, we've done 1. So if we started with 10 grams and we go through one half-life, we'll have 5. When we go through our second half-life, we'll have half of that, which would be 2.5. And then at 3, we would have 1.25 grams of this substance left. All right, next question, they give us an actual reaction. They want us to relate the rate of appearance and disappearance. So we have dichromate. Here's our overall reaction, 14H plus Cr2O7, 2 minus, plus 6Cl minus, and that gives us 2Cr3 plus 3Cl2 plus 7H2O. We're told, if Cl minus is decreasing at a rate of 0.37, then what is the rate of this for appearing? So this is a reactant, this is a product, so the reactant, of course, is going to disappear. The product is going to appear. So negative 0.37 for the Cl minus, and I need to relate the two to each other. That should be 2 Cr3 pluses for every 6 Cl minuses. So multiply that by 1/3, and we should have this appearance or increasing at a rate of 0.12 molarities per minute. And then lastly, question 15 or 20, sorry, question 20. If we have COCl2, that's a gas, and it decomposes to carbon monoxide and chlorine gas. We are told the starting concentrations actually, here, we'll just make an ice table. We're told the starting concentration of the COCl2 reactant. We are not told anything about the product, so we're going to assume the starting concentration for those is 0. We are then, if we want, we could plug in Q. We're going to have 0 over 1.6. We're going to have a 0. Makes sense. Q is incredibly small. In fact, it's 0, so we're only going to be able to proceed to the right. We don't have any products yet, and that makes sense. So we're going to lose reactant, and we're going to form product. Coefficient in front of everything is a 1. My equilibrium concentrations here will be this. Now our K is 8.33 times 10 to the negative 4. I've got x times x, which is x squared over 1.6 minus x. I'm looking at 1.6. I'm looking at my K. My K is pretty small. And in fact, my concentration is almost 5 orders of magnitude greater than my K sub C. So I'm going to go ahead and do the x is small approximation. We'll rewrite x times x as x squared. So if I multiply both sides by 1.6, I'm going to get 0.00133. That's equal to x squared. I want x, so I'm going to do square root of each side. And then x is going to be equal to 0.0365 or 0.037. I could put that over my original concentration and see, do I get something less than 5%? Yeah, that's going to equal 2.3%. So my x is small approximation was okay to make, and the answer there would be D. So that's that for version A. If you have different versions, if the values changed or maybe the letters moved around, but you know the correct answer, you should still be able to figure those out. Sounds like a lot of people are not working those end of chapter problems. I cannot stress enough, you have to work those problems. I would work them for at least 30 minutes a day. I would do that from Sunday through Friday. Try to do 10 or 11 of those end of chapter problems each day. Hopefully this was helpful. Hopefully this lets you know what the right answer was or why it was what it was, and I'll see you in class tomorrow.